Friends, welcome back to another video of the question bank series. This is the grind for BITSAT 2025 wherein we are getting 10 questions stronger in every chapter. Okay, so today we are targeting the chapter of properties of fluids. So previously we have discussed all the previous chapters preceding the fluid chapter. If you have missed out on those, do check out the playlist of question bank series. Okay, let's come to this one. Firstly, we discussed the previous year question weightage throughout the different topics in this chapter. Then we tackle about 10 questions. Okay, so that is the drill of the series. So let us discuss what are the important topics over here. So from pressure, 3 questions were being asked, especially from the excess pressure of your soap bubble and from there. Okay, then we have questions on relative density, only 1 question. Then terminal velocity, 5 questions. Then surface tension and surface energy is one of the favorite topics. So from there we have about 8 questions in the previous few years. Then from the capillarity rise in the tube. Okay, so from there we had about 3 questions. Then the concept of upthrust. Okay, then you have your eureka. Okay, so from there we have 3 questions as well, and finally from the continuity equation only 1 question. Okay, so that was the brief previous year weightage. Let's tackle the questions now. Let's start with question 1 and 2 over here. So in question 1 we have an airplane which has wings of area this, then it is at a level flight at some height. So the pressure difference between the top and the bottom is of the order of 2.5 kilopascals. Okay, you are supposed to tell the mass of the plane. Now the mass of the plane at some level height will be equal to the force due to this pressure, right? So this force due to the pressure will balance the weight of the plane, right? This mg in the downward direction will be balanced by this difference in the pressure, right? The force due to that. Now what is pressure? Pressure is force per unit area. So this change in pressure we can write as force per unit area. Area of the wings or area of the plane is given. So you can find the force, this force, and equate it to mg. That will give you your weight, right, or the mass of the plane. Okay, so from here we get force equal to pressure into area, so 2.5 into 10 to the power 3 kilo, right? And area is 120 meters square, so 120. So we have this, and then this force will be equal to mg, right? G is 10, so you can cancel this out. Okay, now what do you get? 12 into 2.5. 2.5 is like 5 by 2, right? So 5 by 2 into 12, so which is 2 6 are 5 6 are 30. So yeah, so 30 into 10 to the power 3 or 3 into 10 to the power 4. So that is your mass in kgs. Okay, so option B is the correct choice over here. Okay, so just the basic concept of pressure, you have to balance it with the force or the weight. Okay, let's come to this one. Here we are supposed to tell the velocity v3. a1, a2, v1, v2 are given, and a3 is also given, of course. So here we'll use the equation of continuity, right? So you'll see that the liquid is flowing like this. Okay, so we'll say a1 v1 is equal to a2 v2. So this is splitting into a2 v2 plus a3 v3, right? So now v3 we can find. We have all the other variables, right? a1 is 0.2, v1 is 4, a2 is 0.2, v1, v2 is 2, a3 is 0.4, so the velocity will decrease. So v3 will have. Okay, so what can we do? So we can cancel out this 0.2 throughout, 0.2, 0.2, and this will be 2 times, right? Again 2 can be cancelled, 2, 2 and 2 times, right? So what will we have? 2 is equal to v2, 2 is equal to v3, no. So also this 1 is there, right? So v3 is 1 meters per second. So don't do calculation errors, solve it step by step, you'll get to the answer, which is 1 meters per second. This is 1 over here, right? So v3 plus 1, okay, don't forget that. So that is about question 2. Over to the next one. Question 3 and 4 over here. In question 3, we are supposed to tell among the following which is not a streamline flow, which does not depict a streamline flow. Okay, even if you pick out the odd one, you'll say this one and you'll be correct, because the concept wise you can see for an area the particles a particular particle will have one unique velocity in streamline flow, right? So even if you see over here, a particle will have some unique velocity of its own. So here also, each particle has unique velocity. So here, if you see, we have, if we draw an area, you'll see that the particles, so suppose at this point, right? So here particle, this particular particle has two different velocities, right? Even in this direction and that direction, okay? That does not happen in a streamline flow. So this one does not depict a streamline flow. Okay, let's come to this one. Here we have the pressure inside, the excess pressure due to a soap bubble. So the formula you'll know, it is 4T by R. Okay, what is the formula for excess pressure due to a water bubble? Do let me know that in the comment section. Okay, so now this pressure is balanced by an air column of height 2 millimeters. So this is balanced by rho g h. Okay, some density of oil you'll have g and h, right? This column, this is the pressure of this column. Okay, rho g h, right? So we are just supposed to solve for T over here, surface tension, right? So T we can get as rho g h by 4 into R, right? So let's substitute the values. Let's substitute everything in the CGS unit. If required, we'll convert to the, we'll solve everything in the SI unit. Then if it is required, we'll go back to the CGS unit, okay? So density is 0.8. It is grams per centimeter cube. So gram is 10 to the power minus 3 kg, and we'll also have centimeter cube, right? Centimeter is 10 to the power minus 2, and cube, so 10 to the power minus 6, 2 threes are, right? So rho is substituted. We also have a 4 in the denominator. Then G will take it as 10, although it's advisable to take it as 9.8 if not mentioned explicitly. But if you can see, the values are quite apart, right? Orders of magnitude apart, so we can do with that. So we'll take it as 10. H is 2 millimeters, 2 into 10 to the power minus 3 millimeters, right? And R is 1 centimeter, okay? So that is 10 to the power minus 2 in meters, right? So if you see, okay, so 10 to the power minus 3, minus 6, this will be minus 6, right? This will become minus 6, and this cancels out with that. So we'll have 8 into 2 divided by 4, and we'll have 10 and 10 to the power minus 2. So that will give us 10 to the power minus 1. So 2 2s are 2 4s are 0.4, and 10 to the power minus 1, or 4 into 10 to the power minus 2. Okay, here you'll see it is 3.9, basically because of our assumption, right? We took G as 10, we should have taken it 9.8, but that will lead you to this answer, right? And this is in SI unit, of course. We did everything in SI. So if required, we would have gone to the CGS unit of force. But you see that we get the answer, right? So that is about this question. Over to the next one. So question 5 over here, it is a good question. You can pause the video and try it for yourself. It will test your concept of upthrust, okay? So pause the video and try it. 3, 2, 1. I'm going to do it. Okay, so here we have a block of which weighs actually 5 newtons in air, then it weighs 4.5 in a liquid, since there is some upthrust force, right? Once you immerse it in liquid, there will be things way lighter in water, right? When you place them in water. So when it is placed in liquid, there is some upthrust force. You might know its form. Upthrust force is given by volume immersed rho, the density of the liquid into G, okay? So when you have it immersed in liquid, okay? So that is the concept. So first of all, let us, and the specific density of your liquid is given, meaning the density of the liquid divided by density of water. This relation is given. This is 0.5. Okay, this is the definition of specific density. It is the density of the liquid divided by the density of water. Okay, now we are supposed to find the weight of this block in water. Weight in water will be, okay. So first of all, we can use the relation for this. Okay, so weight in liquid we are given, no? So weight in liquid will be the actual mg minus the volume immersed, the density of the liquid into G. Okay, so weight in liquid we are given as 4.5. The actual weight, okay, so it's 5 newtons, so mg is 5 newtons. Okay, so So this is minus this, right? So this volume immersed rho Lg is equal to 0.5. Okay. Now we don't know how much amount of the volume is immersed or the actual density of the liquid, right? We know this relation. Some of you might know the density of water also. So good for you. We will need it. Okay. So let us now try to find the weight in water, right? So weight in water will be equal to, again, the same weight in air minus upthrust provided by water now. So we'll have V, the amount of volume immersed. Again, we are considering it to be same. Then here we'll have water, okay, density of water into G, right? The densities of the liquid in which you are immersing, right? Water, so water, okay. So weight in air we know 5 newtons. Then now we can use this relation to find that, okay. So we know this, right? So rho L in fact can be written as 0.5 into rho omega, right? So you can write this rho L as, okay, 0.5 into rho omega g, and there you see the magic. This and this will cancel, and V rho omega g is 1, right? So basically this value is 1. So okay, so our answer is 4 newtons. Okay, so which is option B. Okay, quite a simple concept. You just had to find the weight in liquid and then weight in water. Okay, you had to use the idea of the specific density. Let me check the answer. Okay, yeah, it's 4 newtons. Okay, so that was the simple concept behind this question. Over to the next one. So question 6 and 7 over here. In question 6 we have a liquid being poured in 3 vessels as shown. So height is same. The height of the liquid in each of the vessels is same. You are supposed to tell the force will be maximum on the base in which of the following cases, A, B or C. Okay, A, B or C. Where will be the force on the base of the vessel be maximum, or all 3 will be equal. Okay. Now it's quite easy if you see. So in each of the case, what is the pressure? Pressure will be rho g h, right? And also the atmospheric pressure, right? P naught, the atmospheric pressure, plus this column of height h, right? And the height h is kept same throughout, right? So equivalent. So this rho g h is same, atmospheric pressure is same, of course. So the pressure for each of these cases is same. The pressure on the base is same, right? And we are also given some additional information that the base area is same. So pressure is same and the base area is same. So P and A, we can write P and A are same. Okay, so what about the force? Force is pressure per unit area. P and A are same for all the 3 cases. So pressure per unit area, these 2 are same. Then this quantity should also be same, right? So P by A, it will be basically FA will also be P by A, here also P by A, P by A, right? So force will be same in all the 3 cases. Basically it comes due to the fact that the pressure is same and they have maintained the area same. If area was different, then it would have been different, right? Inverse relation you'll have. Anyways, let's come to this one. A man sits on a boat of length 2 meters, and this is the breadth. Okay, breadth 1 meters. Okay, so the dimensions of a boat are given, which was floating on a lake. It sinks by 2 centimeter, the mass of the man. Okay, now it's easy. Basically, the water that rises is due to the upthrust, right? It's providing the mass is additional, so mg you can write it equal to this upthrust. Okay, so more mass will sink and you'll have a greater upthrust force, right? What is upthrust? Upthrust is the volume immersed, rho L and G, right? I told you. So the volume immersed is increasing, right? When the man steps on the boat sinks, right? Sinks by 2 centimeters. So the volume that is immersed inside the water increases. Okay, so upthrust also increases. So mg is balanced by the upthrust. Okay, so this is maintained. So mg is now m we are supposed to find, g will take it as 10. The difference is lot. So here u is volume immersed. Now volume you can find length, breadth, and this is height, right? This is the amount that it is immersed. Okay, so initially of course the boat had its own mass, but we are only looking at this now, the new amount that it has sink, right? So that will be equal to the men's weight. Okay, the contributions of the lake, oh sorry, of the boat was already there. Now since the men has stepped on the boat, it has sinked by 2 centimeters. So that is due to the mass of the men. Okay, so yeah, I hope you get the point. So volume immersed is length into breadth into height. Now height is 2 centimeters. Okay, the rest of all it is in meters. So I'll write this area into height. Okay, so this is in centimeters, and then we'll have the density of liquid. Now you're supposed to know density of water is 10 to the power 3. Okay, and of course lake is of water, right? It's not of some other liquid. So density of water is 10 to the power 3 in the SI unit, kg per meter cube, and rho, L and G anyways cancels out on both sides, so we don't have to worry about that. So here it is 4 and 10, right? So this is 10, so 40 kgs. Somebody lighter than me. Okay, so that is question 7. Over to the next one. Question 8 and 9 over here, so they will test your capillarity rise concept. Okay, so here we have surface tension of water being given. You are supposed to tell the capillary rise for diameter. This angle of contact is taken to be 0. Actually water makes about 8 degrees, but here they have considered it to be 0. Okay, it also depends on the if it's pure water or not. So anyways, the formula is 2t cos theta by rho g r, right? So I remember it this way. This excess pressure, what is the concept of capillary? The excess pressure due to the bubble which is formed in the capillary is balanced by rho g h, right? So rho g h is balanced by 2t by r, which was the excess pressure, if you remember. Okay, for soap bubble it is 4t by r, but for water bubble you have 2t by r. So rho g h is balanced by 2t by r. And why this cos theta? Cos theta because we want this r is for radius of capillary. Okay, actually we have radius of the bubble. Okay, so when you write it in terms of radius of capillary, so this r is radius of capillary. Okay, that cos theta factor comes. Okay, so if you want to write it in terms of your radius of the bubble, so this cos theta will. Okay, so that's the basic concept. But anyways, you can of course by heart the formula. So here 2t is 0.06, cos theta, cos 0 is 1. Okay, then rho is, you are supposed to remember for water it is 10 to the power 3. Here they have not given the units for this, but let's take it to be SI. Okay, and G will take it as 10. It won't make any much difference, but 9.8 will give you a precise answer. Then radius is, this is diameter, radius will be half of that, so half, so 2 will go on top, right? So I can write it half over here as 2 on top. Okay, and that is in millimeters, so 10 to the power minus 3. This cancels, 2 2s are 4 and 4 6 are 24, right? So we'll have 0.24, right? 2 2s are 4, and then we have 4 6 are 24, yes, and that divided by 10. So this is actually 0.024. Okay, if you had to take 9.8, that would have given you about 2.44, right? So here if you see, it is actually 2.4 centimeters, right? This is in meters, so shift to powers, so that will give you in centimeters. So if you had taken 9.8, it will give you 2.44. Okay, that's your answer. Let's come to this one. Here we have capillary rise. Now we don't have capillary rise in this question actually. So we have dipped a capillary tube in water or some liquid. Okay, so you note that there is no capillary rise. Basically the water level in the capillary is the same as the water level over here. Okay, so why is this happening? So if you see the formula, 2t cos theta by r rho g, right? So here there is chance of this going to 0, right? All of these are finite terms, but cos theta can go to 0, right? Provided the angle of contact is 90 degrees. Okay, so basically this will be flat to the surface. Okay, the if you see, like if you remember the concept, here we have, if we have acute theta, okay, acute like you, okay, no floods. So here theta, if it is acute, then we'll have h increase, right? And if it is obtuse, it's the concept, theta will decrease, because in the second quadrant cos is negative, right? So there is fall in h, and here there is rise in h. whereas for 90 degrees, exactly 90, the water is flat, so basically you don't have the bubble, right? So if there is no bubble, there is no excess pressure to balance. Okay, so you can relate everything. Okay, so of course you can do it by the maths also. When theta is 90, h is 0, a is the correct choice over here. Okay, theta, remember over here, is the angle of contact between the fluid and the capillary. Okay, so that's about these two questions. Over to the last question for the day. Here we have the final question for the day. Here it is based on surface energy. The energy needed to break a drop of radius r into n drops of radius small r. Okay, so you just break it into smaller drops. Suppose these are n in number. Okay, dot dot dot. So each of this will have radius small r. Okay, so answers are given in terms of n and r only. We don't have to equate the volume or anything as such, which you might do typically. So here what will be the energy? The energy will be nothing but surface energy is basically tension into area, right? So what will be the difference? So in first case we'll have some energy, next case we'll have some energy. So E1 and E2 will have, and then we can subtract those and we can have the energy that is released, right, needed to break. Okay, so delta E will be, we say T1 A1 minus T2 A2. This for this energy and then this. Okay, so the difference in their surface energies will be the energy required to break it. Okay, so here tension will be the same, right? It's the same liquid. Okay, so here tension T is same here in this case. So area is in terms of, these are spheres, right? So area, surface area of the sphere, so 4 pi r square. So A1 is this bigger sphere, 4 pi r square, and T, here you will have what is the area, 4 pi, and okay, 4 pi r square, nr square. So yeah, what is the area of this, all this, right? Not just single drop. So n times the area of one of this. So area of one of this is 4 pi r square. So n times area of one of this. Okay, so you can take common. So 4 pi t is common, and we have r square minus nr square. Okay, actually it will be the other way around. Okay, it won't be this way, it will be this way. Okay, option A, energy needed to break, right? So if you see this one, these drops, you can take a value and you can actually equate the volumes V1 and V2. Okay, you will find a relation between R1 and small r, capital and small r. You will see that okay, you will see that of course this small r is smaller than capital R, and you'll see that this volume, that area, this area on due to the small drops will be bigger than the smaller this area. Okay, so if you find 4 pi r square over here, so r you can find from here, and n times 4 pi r square. Okay, you can take any value of n, suppose 8, that will be helpful. So if you calculate this, this will be higher. Okay, this area will be higher. So actually it's other way around, this area minus this, that is the energy required to break. Okay, so I hope the concept will be clear now. It's not this, it will be that. Okay, okay, if it's otherwise, do let me know why you think so in the comment section. Okay, so that's about today's video. I hope you enjoyed it. Do consider subscribing if you made it this far and align with the vision of cracking BITSAT 2025. If that's your dream, do consider subscribing and check out the other videos that are available that will help you in this journey of cracking BITSAT 2025. Okay, so that's all from me. This is me signing off. Keep enjoying physics.